Okay, in the following example, we are going to be going over something called the shell method. And so what we're going to be doing is we're going to be using kind of like a cylinder, if you will, but we're going to notice that the graph is actually going to be hollow in the center. So I guess let me explain what we're talking about with this cylindrical shell, and then we'll look at it in the context of the problem. So what I want you to understand is that you've got this kind of cylinder, and notice it's got kind of a hollow center, and I am not an artist by any means. I draw terribly. But if you were to, let's say, slice it, let's say, right about here, okay, we're going to slice it, okay, and then we can unroll it, okay. Well, this right here represents, if you think about it, the outer perimeter of the cylinder. This represents the circumference. So what do we say about circumference? It's 2 pi r. Okay, it's 2 pi r. Now it's got some height. So this is the circumference, if you will. All right, it's got some height. We're going to call it, let's say, h. And then it's got some thickness. Okay, and this thickness we call dx. Okay, so if you think about it, we've got 2 times pi times the radius times the height times the thickness, and that right there will give us the volume of what we just laid out flat, this kind of a rectangular prism, if you will. All right, so that's where the formula for the shell method comes into play, and that is that it is the integral. All right, it is the integral from a to b of 2 times pi times the shell radius times the shell height times that thickness dx. Okay, so another way that you could have gone about this is the washer method, but this is just a different method and a way that you can go about finding these volumes of solids. So let's go ahead and take a look. First thing we're going to look at is the graph y equals 6x. And so what does that look like? It's just this graph that goes to the origin. Now we're only going to look at one view of this, and you'll see why in a minute. Then we're going to look at negative x over 6, which is negative 1/6 of x. So it's got a negative slope, and let's say it comes out over here. And we know we're looking specifically where we're going through 1. So let's call this right here 1. So this is like an extremely zoomed in view of this. Okay. So we're looking at this part of the graph, and what we're going to do is we're going to rotate it and rotate it about the y-axis. And so what ends up happening, if I can continue this graph over here, okay, and continue this graph over here, all right, we have this kind of, butterfly looking thing, and if you think about it, it's forming kind of this volume, if you will, a three-dimensional shape as you're rotating it about the axis. So if you notice, it's got that hollow center, and that's what we're accounting for when we're looking at the shell method to find the volume of this solid. So this method is actually really nice. Okay, so let's consider here what we're talking about when we say the radius and all this stuff. So in this case, the radius is going to be measured by this quantity in this direction. And so when we go out that many units, we're going to call it x. That is our variable there, our radius. Okay, it is x units in radius. Okay, but it is the height that we really need to concern ourselves with. And the height we're going to take from the functions themselves. So this one was y equals 6x, and this one was y equal, let's see, negative x over 6. So this height is this right here, represented by the following. So let's take a look. It's going to be, let me clean that up. The height is going to be 6x minus negative x over 6. And of course, we're going to combine like terms, and they are actually both like terms. They're both linear. So you basically have 6x plus 1/6 of x. You're going to end up getting something like 37 out of 6x. And so that's the height there. So we've got the radius. Okay, it's x units. All right. We've got the height. it's 37 over 6x. And now we're ready to put it all together and then integrate. So let's go ahead and take a look at the volume and what that would look like. Now, we are going to go, in this case, integrating from 0 to 1. Okay, so integrating from 0 to 1, we've got 2 times pi. Again, we said the radius was going to be represented by x units because we're x units away in this case from the origin. That's our variable in play. And then, of course, the height represented by 37 over 6x, and then our thickness dx. Okay, so we've got that. We've got not much left to worry about here because it's just a little bit of algebra. So from 0 to 1, we're going to write the 2 pi on the outside. We're going to have 37 over 6x squared dx because we're going to multiply these two. Now we're ready to integrate. So here's the calculus part, if you will. 2 times pi, then multiplied by, well, we've got 37 over 6, and then the x squared becomes x cubed over 3. Okay, evaluated from 0 to 1. And this one's rather nice because of the fact that you're plugging in 1 and you're plugging in 0. 0, really, we don't need to plug in because we're going to get 0. Okay, but the 1, when we plug in, that does come into play here, but it's actually really easy to evaluate because it's 1 cubed over 3. And then, of course, we're going to subtract 0, but again, no consequence there. All right, so basically we have 2 times 37, okay, 2 times 37 times pi divided by 18, okay, so let's write that out. 2 pi times 37 divided by 18, and that's really easy to reduce this fraction because you end up getting 37 pi over 9, and this is cubic units again because it is a volume. All right, so that's what we get there. All right, so nothing to it really. Really nice problem, really nice example. Let's go ahead and take a look at one more example of this shell method, and I think you're going to see that it's actually really nice and really easy. So hopefully it's understandable. All right, give me 1 second. Okay, so here is the next example. It's y equal 9x squared and y equal 9 square root of x. And again, we're rotating this about the y-axis. So let's go ahead and take a look at what this looks like. We're only going to look at one view of the first quadrant, and then we're going to rotate. So let's see here. First thing I'm going to graph, easiest to graph, 9x squared. It's a parabola right here. Okay, and then 9 square root of x is a square root function, and let me color it in a different color, suppose like that. Okay, so what we're doing is we're going to be looking at this right here, and basically the volume that it's going to be forming as we rotate it about this y-axis. And so let's go ahead, and I think I can try to attempt to draw this in maybe some kind of 3 dimensions. Let's see. Well, maybe not necessarily. It's still flat. But again, it's a terrible drawing, but you get the picture. Okay, if you're rotating, it kind of looks like a bowl, if you will, a bowl that has some thickness inside of it, and basically we're finding the volume of that bowl. Okay, so that's what we're looking at again, and again we're going to apply the shell method. So our job first to figure out, the height, the radius, and all that good stuff. Well, the radius again is no surprise here. It's x, okay, because we're going out x units. Okay, so that's going to be pretty standard. All right, what we need to figure out is these points of intersection, and that one right there is 0, 0. And you'll see there on the next one, you can set these two equal to each other and solve, but you can also find this on the calculator, if you will. 1, 9 is the intersection up here at the top. So we're going to basically be integrating again from 0 to 1 in this case. All right, And let's see what this looks like here. If I find the volume, it's going to be 2 times pi, and again from 0 to 1. We need the shell radius, which in this case is x, and what we need now is the shell height. And so that's what we need to come back and list or write down. So this right here was y equal 9 square root of x, and this one down here is y equal 9x squared. So the height, if you will, is going to be 9 square root of x minus 9x squared. And it looks just like that. Okay, so now we're going to write that in. So let's see, 2 pi x, and then I'm going to multiply by 9 square root of x, which 9 square root of x is, let me rewrite that, pick a different color, 9x to the 1/2. So I'm going to clarify there so that you see why I'm going to write 9x to the 1/2 over here. All right, 9x squared and then dx. Okay, so we've got that down. We're going to distribute that x across the board here so that we can make it very easy to integrate. I'm going to factor out again the 2 pi. That's okay to move across the integral. X times 9x to the 1/2 will yield 9x to the 3 over 2. Remember, when you do that algebra, power to a power, a power times a power, you're adding the exponents. And then, of course, minus 9x cubed. All right, nothing to it there. What do we get? We get 2 pi. We get from 0 to 1. Let's see here. Actually, no, we don't need to write the integral anymore. We are ready to integrate. All right, so 9x to the 3/2, you're going to add 2 over 2. That's going to become 5 over 2. So then you're going to multiply by 2 over 5. Okay, nothing to it there. And then minus, and then the next one is 9x to the 4th over 4. And then evaluated from 0 to 1. Again, 0 really nice because it's just going to yield 0 when you plug in. Here we're going to have 2 pi. We're going to get 2 times 9, which is 18x to the 5 over 2 divided by 5 minus 9x to the 4th over 4. Again, 0 to 1. So we're almost done here. We have 2 pi. We're going to have 18 times 1 to the 5 over 2 divided by 5 minus 9 times 1 to the 4th divided by 4, all minus 0, because that's what you get when you plug in 0 into both of those. So let's see here. We have 2 pi. All right, plugging in 1 is really irrelevant. You have 18 over 5 minus 9 over 4. All right, you do that quick math. You get 2 pi times 27 out of 20. You do the simplification there. What do you get? You get 27 pi out of 10, and this is units cubed or cubic units. Again, I'm not going to really write that, but it's a volume, so you know that the units are cubed. Okay, so again, another really nice example of this shell method, if you will. And think about it, you know, you're taking this kind of cylinder, you're kind of unraveling it, but it does have a thickness, so it's not entirely flat. Okay, and that's what we're doing because we know that it's hollow in the center when we rotate these things. So 2 really nice examples of shell method. As always, I hope this video was helpful, and remember, like and subscribe.